Now we understand it, and now that the ice and snow is gone and the fields are starting to dry, we've got the opportunity to get this in before application of any slurry starts to happen. So some of the other sampling, we're also sampling a ephemeral stream and a spring. We know that water is obviously, if it's not running off, it's going down, so we've found a few springs, we know they're all over the place. We'll hope we'll find more, but we're going to monitor a spring that's near one of the application fields and look to see if it's moving down with the monitor from that spring. So this is upstream, one of our gauging stations, upstream. This is the downstream one. And again, USGS are going to help us gauge this station downstream. We've got permission of the landowner that lives on the other side of the creek that, for one reason or another, is concerned about this. And so we will be sampling here and at the same time getting flow by USGS. This is the spring. Just gives you a visual idea of what it looks like and where these sampling sites are. We captured the farm above and below. Obviously, there's other things going on in that reach. With the Mount Judy, I wouldn't call it a city, but the town of Mount Judy is also. So there's other operations going on, but that encapsulates above and below the farm. There's a spring. This has been there a long time, many, many years. And it's typical of a lot. You can see they've got this trunk. Basically, this is being used by the landowner for a watering source for his cattle. And it's kind of gone out a bit of it out of disrepair. The water's wet. You can see about the top there where it's a bit wet. But the cows are hanging out there because it's in the summer when it's dry and it hasn't rained for weeks, even sometimes months. This will still be flowing. And we found that even at our sites here where we've done the same type of work at Savoy watershed, that these things will flow out in a drought. Water is moving, and it's still moving when you think there isn't any water left in that piece of ground. It's coming from somewhere. But anyway, so we will, we've been taking ground samples of this. Eventually, we plan to put a monitoring a sample. I'll show you what one of those is, to collect samples when this starts to peak. So this is some data, again, it's in the quarterly report, but I've just kind of abbreviated it for you to give you an idea of some of the data that we've collected, and it's out there, as I say, it's on websites, many different sites, but it gives you some idea of the dissolved phosphorus. That's probably one of the more critical things in terms of plants on the ground need phosphorus in solution. They can't find it. We know that most of it, we used to be taught, back in the old days, and the gentleman here that used to work here, Tommy Daniel, was taught that many years ago in Wisconsin, that phosphorus stays in the soil, money in the bank, it never goes anywhere. Well, we know that's not true. If it gets enough, it's a bit like a sponge, it gets saturated, it starts leaking. Plants can only get what's in solution, it can only suck it up out of the ground. It's the same with plants in the water, algae. They can only see dissolved phosphorus. The other stuff's there and it will change to dissolve eventually, but they can only get that. So that's what is probably one of the more critical measurements that we actually determine, is the dissolved phosphorus. And you can see this is upstream, downstream. You can read, I won't repeat it, but it's quite variable. I mean, the dissolved phosphorus is very low. I think if we measured in tap water, we might get down to about 0.003. I think our detection limit, and Brianna, I know you're here, you do a lot of the testing, the limit of detection is pretty close to about being 0.002 or something like that. It's pretty low. And so basically what we're saying is not much phosphorus in these samples. Oliver, to the end? Can you vote?
Sure. Well, I may forget about it. I'm just wondering why October 15th, the storm event.
No reason. I tried to pick out a month spacings. Just tried to pick out month
Phosphorus and E. coli were much higher on the flood or the storm.
Yeah. I was just picking out a month reason. No specific reason. I tried to pick out 4 weeks intervals, and you're right. But in defense of that, this was the highest number we ever got. And that's downstream, 17,000. So that is a high one, and I think it's higher than maybe the one on the 15th. That's downstream. Nothing has been applied to that farm. I think the first application was on December the 30th. So, and we've got other data, other people have done data and collected data and shown it. So this is basically getting as baseline. But one thing it does show is that you know, there is other sources, or there is some variability in the concentrations coming down. Some of them are low, some of them are high, and so we have to recognize that. But the levels of nutrients that we see here are typical of these fairly pristine type of watersheds. Spring, it's similar. Again, we've got on this 15th, you're right, we've got a high bacteria here. It's in the spring. I'm not going to interpret where that came from because we're just presenting the data here. Obviously, there's more in this date than there was the week, 2 weeks earlier. And that's in the spring. You saw that spring is covered, actually there's a plate over that spring, that concrete hole is covered with a metal plate and stone, so nothing can actually get into that hole where we take the sample. In between sampling, it's covered. Now we're also now monitoring one of the ephemeral streams. This is downstream. It crosses the road, the track below the farm operation. So this basically is a little watershed that drains that area where the farm is. We have this culvert that goes under the road. We can use that as our flow monitoring device by putting equipment in here at the bottom, which will record the flow. It measures the velocity of water moving through there, so we can determine how much water. And we have another sample there that will collect this sample of water once it starts to flow. We can't get out there quick enough to collect these storm samples, and so this is a way that's tried and true, tested, to collect water samples. They're triggered by flow. When the flow starts, they start collecting samples. So we get real time, we can get cell technology that will tell us if it's starting to sample, and then we can go out and collect the sample within that required period of time. So that's the type of technology. And this is the installation that's there, that's sitting there, going to be collecting these samples with a solar panel to power the battery that powers the auto sampler. And this is the auto sampler. It's an ISCO sampler. Basically, there's two makes. This is one of them, ISCO and the standard sampler. They're standard technology. Everybody basically uses them. In here, there's 24 bottles that collect a sample. It's got a computer in there that when the flow rises, it'll suck a sample, and it'll suck so many mils, and we tell it how much to do that, and it'll empty into a bottle. As you can see on the right, that's one of the flumes measuring the flow, or when the flow goes through there. When I first started this, we didn't have this technology, and we had to get out there, you had to stay out there. When you thought it was raining, you had to wait, or you had to try and get there in time. These things are really flashy. We talk to USGS, and they say that stream will come up within minutes. It will go from being a nice trickle to a huge torrent within a matter of minutes to hours. And there's no way that we are going to get out there, and if we could get out, we might be stuck on the wrong side. But this allows us that technology to collect those samples, because we know we've been going out there and getting base flow samples. Base flow samples will get us what's there in base flow, but it doesn't tell us what's in storms. And other processes occur during storms, other pathways, other losses might occur, and so we've got to get storm samples as well as base flow samples to have that science foundation here. What are we going to do about the water? Made the point earlier that water is moving into the soil. So this is the type of thing that isometric altimeters does the same, different terminology, but basically allows us to collect a sample from down in the ground. If you put these in properly, they do not leak water. It's like putting in a well. If you put the well in right, water's not going to seep down the outside and pollute your drinking water supply. So we pack this with tensionite and clays that will stop water moving downside. So the water that we're collecting, one at the shallow one, and then one at the deeper one, and we pump it out. And we'll collect samples in the water. So we know, we can get an idea of what's going down there. The blue one is telling us water, what's water there, and that will tell us where the water table's vary. Is it coming to the surface? Is it so that feels saturated? Is it any more rain? It's going to wash off. Soil can't hold anymore. So where that water table is in that soil, that's all going to be very important in helping refine nutrient planning on this farm or other farms. So that's our little box. We don't want people getting in, we don't want critters getting in, they've got to be covered. But again, I mentioned we're there because the farmers have allowed this to be on there. And so they don't want this sitting there and they can't cut hay or the cows are going to trip over it. So what we've done, Carl and our engineers, got better minds than I do, will bury it, like, a bit like what you've got at home on your water meter. And we'll get these plastic containers which we can bury in the ground, and basically this equipment just sunk into the ground. And so we'll seal it off. And they'll do the same thing as what normally folks do at the surface. We'll have to bury it because otherwise we can't do it. We've got to bury it to retain that, ability to be on those farmers' fields. And so what we do is, you go in there, and you take the cover off, and then you put it back when you finish. And these are strong enough, round enough, that a tractor can go over it, cut hay, do whatever you want to. Obviously, we'll have a GPR or a GIS, because we'll have to go back and be able to find these again where they are. I mean, it sounds, you know where it is, but 20 acres, you could probably lose one or two of these. So we have got GIS, technology, so we can go back to the same spot. So that's how we propose to look at monitoring the water that may be moving through the soil and collecting samples of that water as it moves through the soil. This is field 1. That's where our flume is. We've looked at where the water is flowing. That's where it's leaving this field. This is a steep slope here. The slope is about 3% here from that soil map, and it gets steeper down there. And so water exits this field here. And there's a spring here. This is the top field. It's got fairly thin soils. We don't think that we need to be measured because it's steep slopes. We don't think that the water's going to be moving through here. And plus, we've got so many down rocks up there that we don't think we can really put that technology there. Field 12. This is where we think the water's moving. If it does move in a large flood, we've got that same monitoring device I showed you with that sampler. It sits there in the field waiting for water to come off into the creek. When it does collect samples, we go back, collect them. And then we've got these piezometers, or these monitoring wells, that would be in transit. And because we've got that ground penetrating radar, we can go back in and start to put these monitoring wells either where there's that chert layer or where there's that discontinuity. So we know now better where to put these so that we can measure or capture where one might think if there's a risk that we've got these in the right place. That was one of the things that's taken us time to be able to get to that stage, to feel more comfortable, so perhaps there's some logic to why these are there. And this is field 5. Not going to be, now everybody knows, most of you, that that's not going to be permitted now at the moment to apply. We're still going to continue to monitor because we feel this is a good baseline. This landowner has been putting fertilizer, growing hay, feeding cattle. It gives us a baseline for what's coming off of these fields prior to. So we will continue to do this careful monitoring on this field. We don't think that is a waste of time. We think it will be valuable, as I say, in getting a baseline. So getting close to the end now, looking at the sustainability of the whole system. We've talked a little bit about what's happening on the field. We want to minimize finding any impacts as soon as they occur and let the appropriate people know that there is that issue. And that if there's an issue, things are done to change that. But the long-term thing is looking at the sustainability, not as just this farm, but any other farm like this that may be landlocked or has manure that is, as I say, manure is not a waste. It's a resource that our farmers will use it, not just for nutrients, they use it for the organic matter. Most of you are told to be poor. They're poor because they don't have a lot of organic matter. The main thing about manure is it gives a lot of health and microbes and organic matter to the soil. So a lot of farmers like it because of that. Commercial fertilizer doesn't do that. It only adds the nutrients that plants need, but they need other things. That the organic matter helps hold water. It makes it soils retain more water, so they're now address droughting. So, as we like to say, it's a resource. So some folks are going to use it. And so we're looking at manure management, looking at solid separation. We've done some work. I haven't. Carl is braver than me to actually go out on a boat on the manure pond and take samples of the manure. As I said, it's a field work. It's a fun job. But we do it because we enjoy it and because we're researchers and extension, basically. And so the stuff has got different properties of manure. Some of it settles to the bottom, and so we know the heavy stuff settles to the bottom. We've done analyses, and so it gives some chemically enhanced treatment. There are ways of doing it. Our other farmers have done it. They leave the systems and they don't work after a while because they go and grow fine the chemicals. So we've got to figure a way of getting locally sourced chemicals that can do that same thing, possibly. And that would be a really beneficial finding for a lot of farms if we could make this chemically enhanced separation work in this local setting. Because I can guarantee you go and ask you will not find many farms that can make this work because it's just not economically feasible. And most of us in this room are not willing to pay the extra 5 cents or whatever on their chicken or meat to offset some of those technologies. So, the manure export, again, getting it off the farm or getting it out of the watershed. That if you separate it, you can get most of the water out, so you're not sucking out water, you're sucking out nutrients. And we're going to look at the economic considerations. And that's the main point of this, so it makes it relevant to other farms as well as a sustainable operation, if this farm is that sustainable. I'm not saying it is or it isn't, but economically that is, and whether it's regulatorily compliant. So this is all part of this sustainability program that we're hoping to put in place, at least assess if that can work in this farm. And so, if you're a farmer, it's a juggling act between producing, getting enough food for those cows to eat, for the meat produce, or else you want to protect the environment. So it is a balancing act. And hopefully, obviously we won't solve this. We're not that naive, but we hope that we'll provide some science to go a little bit further along this pathway of getting this sustainability. And so this is some of the work that, as I say, Carl, that you can see this is in the manure in that's in the pit, the nitrogen and the phosphorus. The blue is at the bottom, the green is at the top of the pit. And so the nutrients sink to the bottom. There's more at the bottom than there is at the top. And the other important thing is there's more phosphorus relative to nitrogen in the bottom. So that's a more valuable resource in terms of market value of somebody, if you can get it to sell to somebody. So it gives them a management flexibility. So, one simple thing is that if you can get off that top water, which has got possibly less phosphorus, it's got nitrogen, that allows you to maybe apply it on fields where you don't need that phosphorus. And then it gives options. But the point is that the separation gives us some opportunities for treatment and treatment of that manure to be able to turn it into something which might have some value down the road to somebody else. And so it's looking at the flexibility of the system, chemical manure treatment, export, and getting it off the farm. So what next? That's kind of giving you an idea where we are. We're putting in field monitoring equipment this week to look at those fields while the weather's good and before many more manures apply. We're getting an external panel to come in and review us and see what we are doing, what we've done. We feel we have expertise. We showed you right at the beginning what we have, but we don't know everything. We're not that egotistical to think that we have all the answers. And so we are bringing in people from outside of the state that don't have any vested interest in this, that don't basically work with us, to come in and assess what we've done and look at this, and hopefully, if there are things that, you know, that other people have suggest they can do, we will put into operation. So we're going to go through that review panel. We will do some dye tracing studies and also some natural chemical studies. I think one of the things that we wanted to do before we jumped in and did a dye tracer is, where do you do it? Now that we know that these things with the GPR and where the fields are and what they look like underground a little bit better, we have a better idea of where to put the dye and where to measure them. So that we'll actually get some value from it. We know when we put a dye in a sinkhole, it's going to get out of the, we're going to find it. So we know we need to, now that we've got better knowledge, we can do that with better understanding. And there are some things naturally, boron, vanadium, lanthanum, that are naturally there that can help us age that water. And so we can measure those on these samples. We've tried it out at Savoy, we know it works. Some of them are dyes that you can add, and some of them, as I say, are naturally there. And so we can start to source some of these waters. We can do some fingerprinting. We can measure what's in the creek as we go down the creek. And we can look at temperature differences. If there's a lot of, if you're going down, floating down that creek and it gets cold, all of a sudden, obviously there's a lot of groundwater coming in from somewhere that's cooler into that creek. That tells us where you are there, and there's a source. And so those are the sort of things we can do. Some of the things that other chemicals are in there that will help us do that. Boron is it's in households. Ag don't use it. So, you know, there's a lot of natural traces out there that we can look at, not just how much is there, but ratios. So there's a lot of, as I said, science that we can apply to this. Looking at nutrient mass balances, we want to know how many nutrients actually being applied to the whole of that watershed, where they're going, and look at some mass balance. We also want to do, we will be doing a biological assessment of the whole watershed. How does this watershed fit into the other watersheds in the big creek? How does this fit in there? So the biological assessment. We know that that there are nutrients and in the stream, and we have standards, but do we see the expected biological response that everybody in this room is concerned about or not? You know, you can have that chemical in there, but you get a response for different reasons. If it's shady, if there's a lot of trees around creeks, it doesn't get any sunlight, so nothing invasive. You can grow as much. If you clear that riparian area, you don't have a lot of trees. You get a lot of sun. So there's a lot of other things that help determine whether those chemicals are going to cause a biological response. And the biological response is what most people, I think, are in this room for, because that's what they see and that's what affects them. And I'll close with a couple of pictures here that Barbara Hinton allowed me to use, and just use for this, but there were some pictures that she's taken of Big Creek. I think she does have a website, and actually she sells them if you like them. But anyway, I allowed us to use some of these. It just shows some of the pictures of Big Creek, and it's natural beauty. And with that, I will close.
I'm going to ask the rest of our panel,
I would like to know, I guess it's easy, the external panel and review, where is that coming from? Who are those people that are a panel? Where do you draw them?
the question is, who are the expert panels, where do they come from? And I think Andrew would be the most appropriate person.
It's from the scientific community who are experts in different areas. One is looking at nutrient management, one is a hydrological expert, one is a karst expert, and one is a manure management specialist. We basically asked other people who they would recommend. We didn't select them. We asked people that externally, basically.
Can I guess what I wanna know is, I know that scientists work in every field. Lots of huge corporations such as Cargill has scientists working for them. I'm not saying that that was done. I would just like to know where the panel comes from. If this scientist is from there, who does he work for?
Right.
If this scientist is from there, who does she work for?
Well, yeah, I mean, that will be public. You know, they're not, it will be public, and it's gonna be towards the end of next month. I can tell you that two of them coming from the U.S. Department of Agriculture, one's coming from, I think he wears at the University of Kentucky hat and a consultant hat, but he's a university employee, and the manure person is also a university employee in North Carolina, where they have a lot of hogs.
Right.
Specific to this. So,
Thank you.
yeah,
Next,
thank you.
next, please.
Do you think a nutrient management plan based on the phosphorus index that measures the first 4 inches of soil for phosphorus is a workable plan in a karst watershed?
That's part of why we are in the watershed doing the assessment. The other thing that you have to realize is in a karst topography, as we showed in the presentation, there is karst topography there, but it's under a layer of soil. The other thing added to that is as you apply phosphorus to the soil surface, which you do with the manure application, that soil surface phosphorus migrates downward as only its soil particles saturate and move down. So that top 4 inches is a better representation of environmental risk than the top 6 inches or the top 8 inches. So that's the answer in the direction you're going. I think that's probably sufficient.
And I think there are other safeguards in place in terms of the, not just nutrient management plan, but in the CAFO plan that go precede. I mean, they over, you could probably better say that.
Well, I think the other thing you need to think about or remember or become aware of with the phosphorus index, it's not just the amount of phosphorus that's in the soil that is considered. It's the amount of soluble phosphorus in the manure that is applied. It's the amount of total phosphorus in the manure that's applied. It's the type of vegetation that's growing. It's the type of agricultural practices that are taking place. The cattle management enters into it. The soil types themselves. So it's a complete matrix trying to assess the risk.
One follow-on question. Obviously, the soil accumulates phosphorus that is not utilized by the plants. I believe I understood you all to say that eventually it is all soluble and dissolved, and therefore goes into the groundwater one way or another. What is not utilized by the plants also migrates eventually down into the groundwater. So I do not see that a nutrient management plan based on phosphorus index as it has been given to the ADEQ to administer is a sound plan. It's got more holes in it than pores in the soil.
Well, I won't go into the, sorry, I won't go into the details. I'll get into that, you know, because that's beyond what we, you know, with the science. But the point, the one I would correct you, I guess that's not quite right, I apologize, but is I did say that it builds up in the soil, and it's when eventually, it's not all soluble, no. There's a lot of minerals, iron, aluminum, calcium, or whatever, that will bind